All right, so I was looking over this SRT logo right here, this one, and I noticed a couple of problems with it. I think it misrepresents organic chemistry and SRT as a whole. So I figured rather than tear down a fellow member of the scientific community, we could instead lift them up and give them some pointers on how to make this molecule better represent SRT. So let's begin with some constructive criticism. First off, the most atrocious part of this molecule, these right here, these little nubs on the end. No, they're not working for me. You know why? Because in a skeletal structure, what these lines represent is a bond between two carbons. Now, by putting these nubs here, you're putting a bond in between two bonds. How does that make any sense? That doesn't make any sense. The only time I've ever even seen it happen is in polyhaptoligand bonding. Here, I'll give a quick representation of that right here. You got a carbon that's sp2 hybridized, so you got the little hybrid orbitals. It's bonded to hydrogen up here, and it's got an orbital bonded to another carbon. I'm not an artist. Every prof will tell you that, especially not me. So you have these, and these are sp2 hybridized, so you have the leftover p orbitals that aren't hybridized. It's my best drawing of a p orbital. And they're pi bonded to each other. And then what happens is you have your metal over here, and it has this dz squared orbital that comes in like this. It says, hey man, that's pretty cool, and it actually bonds right here to the middle of these of your two p orbitals. So the point is that this only happens in organometallic chemistry, and we represent it like this. That's how we draw it for organometallic chemistry. But look at this. There is absolutely no freaking metals anywhere on this. Everything here is either carbon or hydrogen. So we need to fix that. So we're going to go ahead, take this little red out, remove the marker, or remove the nubs on the end. Second problem. Anyone with eyes will realize what the frick is going on with these. Are they benzene rings? They kind of look like benzene rings to me, but they're these weird, configurations that have like two double bonds right here. Like, what's going on right here? Let's replace them with something that's more recognizable and just make them benzene rings like this. Boom. Either do it this way or this way, but I think we're going to stick with this because this is more recognizable. You look at this and you say, oh, that's a benzene ring. This, you kind of look at it. What's going on with this circle in the middle? I don't know what that circle means. I haven't gotten past the Gen Chem, so I don't know what that is. So we're going to go ahead and make sure these are benzene rings. And while we're at it, look at this carbon right here. That's got 1, 2, 3, 4, 5 bonds, 5 covalent bonds. That doesn't make any sense. Carbon forms 4 covalent bonds. You're destroying the octet rule. You're destroying chemistry. Let's get this benzene ring out of here. And while we're at it, this, what I think is supposed to be cyclohexane, is just not going to work here. It's too overcrowded. It's adding on all this. Then we got to go through and add the little chair structures. Look at this chair structure that I'm going to draw, if I can remember how to draw one. Then you got to flip it, and all your axial hydrogens and substituents become equatorial, and it's a whole thing. And it's just going to mess with. It's just going to overcrowd it, and that's not what we're about here at SRT. So let's remove this. Now let's take a look at this molecule that we have left over, because all this red marker can get in the way. So we have a little what is this? 1, 2, 3. A little butane right here attached to a benzene ring. If I can draw it. Attached to a lovely benzene ring, and then we have another methyl right here. It's getting a little better, but look at these. Look at this butane right here. Where's my 109.5 perfection that I expect from sp3 hybridization? It's not there. We need it there. So what I'm going to suggest is that we make this look a little more palatable to your average, average chemistry student. So instead of doing this, we go through here. I'm gonna delete this with my Control Z. We're gonna draw our benzene ring, and then we're gonna go ahead and add the little butane on. Oh, voila! That looks freaking awesome. Oh, we're missing one. Oops. Right there. And then we have this little methyl group on the end, but I feel like it takes away from the overall picture. We're kind of getting too focused on this benzene in the middle here. So let's put it like right here. Oops, I hit something on my pen. Let me fix that. Let's put it right here. Okay, it's starting to come together. But you notice something about this molecule? Where are my electronegative atoms? Where are my my non-carbons, my atoms that really make up organic chemistry and allow for more advanced functional groups? So we need to include this. Maybe we could do oxygen, maybe like a halogen like fluorine, chlorine. Oh wait, I know, we can do something like pretty common. We can put in amine functional group on this. Oh, perfect. I think we have it here, guys. We have the perfect SRT organic molecule to represent SRT as a whole. I'll put a little, do this little banner thing you have here. SRT. Oh my God. This is perfect. I think we have the best organic molecule right here. Actually, you know what? I'm not familiar with this organic molecule. Let me look it up. Hold on. Oh, that's a cool name. It's called methane, 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 fet, amine. Oh, because the amine. Oh, it's called methamphetamine. Oh, this molecule is perfect. This methamphetamine molecule perfectly summarizes what SRT is all about. It's not too complicated, but it goes in depth. Truly amazing, guys. Truly amazing. Thank you so much for your time.